Hey guys, I'm live. This video may be a first for me. It's about a subject that I studied and know something about, but I've never done a video about on YouTube or anywhere really. I'd like to discuss modern physics. I studied physics in Harvard College. I was an engineering major, but I did studied math, physics, chemistry, engineering, computer science, and various humanities and social sciences such as psychology, music theory, took physical education. I took, whatever. I took rhetoric, which is how to write, words, whatever. But not write physically, but write papers about books and stuff. But anyway, I like to discuss modern physics. So, modern physics is in two categories. The very small theories for the very small things, which we call quantum mechanics, and theories for the very big things, which we call relativity. And it turns out that if relativity is correct, then quantum mechanics is incorrect, and if quantum mechanics is incorrect, then relativity is incorrect. So, thus, the lack of a unified field theory or theory of everything that would either reconcile quantum mechanics to relativity or eliminate one and say that the other is true and applies to everything. Neither of which has been. The theory has not. The search for the theory of a unified field theory has not been successful yet. But there have been several good attempts, such as string theory, M theory, or superstring theory, membrane theory, which can be called M theory, and so on. But rather than talk about those two contradictions, or that contradiction of those two things, I'd like to talk about some of the specific things about quantum mechanics and relativity that I learned and studied. So here goes. So in quantum mechanics, there's a thing where particles can change position in zero time. In other words, a particle can go from one position to another without ever having traveled in between. It never was in between the two positions. It just was from one and then instantly at the other. And that's why quantum means quantity or a set value. The particle doesn't move through space to get to the other point. It just becomes that other. It just appears at that other point and disappears at the first point simultaneously with zero time. And this is the phenomena of electrons, protons, neutrons, subatomic particles. They don't travel in the way we think of this continuous, time travel, travel. It's discrete. It's jumping from level to level in zero time, and thus it really is counterintuitive to our what we call normal world or normal reality, because I don't just go from New York to San Francisco in zero time without ever having traveled in between. Atomic and very small particles can do this and do this. Now, about relativity. Relativity is about large things. So there's a thing in relativity where space is actually interchangeable with time. If you travel through space, you actually travel through time at a different rate than if you don't travel through space, or if you travel through space at a different rate. In other words, moving through space makes you move through time slower. And yet, nothing is theoretically, according to Einstein's theory, able to go faster than the speed of light. But if something can go something is traveling at the speed of light, time stands still for that particle or thing. In other words, at the speed of light, time doesn't travel. Time doesn't exist. Things just stay. If I could travel at the speed of light forever, I would never age. I would always be whatever age I started traveling at the speed of light at. But yet that itself is a contradiction, because according to Einstein's theory, nothing can travel the speed of light unless it always has traveled the speed of light. Nothing can speed up to the speed of light. Nothing can go faster than the speed of light. And the only way to be traveling the speed of light is if you always were traveling at the speed of light. You can't, once traveling at the speed of light, always traveling at the speed of light, or at least once not traveling at the speed of light, never travel at the speed of light. You can't accelerate to the speed of light. You either are going there at the speed of light or you're not, forever. and nothing can go faster than the speed of light. And theoretically, if something can go faster than the speed of light, whereas if something is going the speed of light, time stands still. The theory is that if you could travel faster than the speed of light, which they call warp speed in Star Trek, you could actually go backward in time, because you're breaking the light barrier, and time would actually go backward if you could travel faster than light, much less accelerate. Not only to the speed of light, which is supposed to be impossible, but even accelerate to past the speed of light, time would go backward, and you would have a time machine or time craft or spacecraft, time going backward in time. So there's that. And then there's something about pairs of. There's something a guy named Heisenberg. I forget his first name. Oh, I should know. Something Heisenberg. I don't remember his first name, but he had the Heisenberg uncertainty principle. The Heisenberg uncertainty principle says that, this is a quantum mechanics theory, that there's often pairs of phenomena where if you know one of the pair, you cannot know the other one with perfect certainty. And such pair is position and momentum. So it's the atoms, such as protons and electrons and neutrons. If you know position, you cannot know its momentum. Momentum is mass times velocity. So momentum is a mass with a vector velocity, with a vector velocity's vector of magnitude direction. So when we speak of velocity, it's not just a quantity of magnitude, it's also a quantity of a magnitude and a direction. So velocity is actually how fast you're going in what direction. And then when multiplied times the mass of whatever is being moved, whatever is moving, that gives you the momentum of that thing. Now, if you know the momentum of a subatomic particle, which means you know it's how big it is and where it's going, you don't know where it is. You don't know position. You cannot know position with certainty. On the other hand, if you know the position of something, certainty, you cannot know its momentum, or you cannot know its velocity, or mass and velocity combination. And this is interesting. In Breaking Bad, Walter White takes the name Heisenberg. Say my name, Heisenberg. That's the same Heisenberg that made the Heisenberg uncertainty principle. Now, I've heard of something I've studied called quantum creativity, and about the mind, the way the mind creates and functions. And often the mind is much like an uncertainty principle, because try this out. You cannot know what thought you're thinking and where your thoughts are going at the same time. If you think of what thought you're having as position and where your thoughts are going as momentum, if you know what thought you're thinking, which is like knowing position, you cannot know where your next thought's coming from. You cannot know what your next thought is. However, also, if you know what the direction of your thoughts are, the momentum, if you know where your thoughts are going, you also at the same time cannot know what your thought is. You can know what your thought is, or where your thoughts are going, but not both at the same time. And similarly, you can know velocity of something, and you can know its momentum, but you can't know velocity and momentum with absolute certainty at the same time, and on the subatomic level of mechanics. So there's that. Then there's also something about observation and reality. Things change when they're observed. You can't measure a quality. You can't measure something without also changing that whatever you're measuring. If I look to see how I look, I'm also changing how I look by checking how I look. I look how I look differently when I don't check it than I do when I check it. And because once you observe something, it becomes observed, and it changes what you're observing actually changes the fact that you observe it. And this is often thought of it in the example of Schrodinger's cat, where if you have a cat that's been poisoned and it's in a box where it can't be observed, the cat can simultaneously be dead and alive at the same time, and yet be both dead and alive. But once the box is opened and you observe the cat, you cannot observe a paradox. So the cat either becomes dead or becomes alive once you observe it. But before you observed it, it was neither dead or alive. Like I can, interesting. Observation actually changes what you're observing. It's a principle of quantum mechanics, and it also similar in magic and in karma, in actual real life, I think, because if you give something energy, you're observing it, it changes what you're observing. So this is the principle of magic. If I observe in my mind or think in my mind of being rich, it changes whether I'm going to be rich or maybe even am rich. Well, visualization is based on perceiving something, measuring something in advance that then changes what you are measuring or thinking of so far as what happens. If I visualize being rich, I already put into action that I might be rich. Whereas if I didn't visualize that and nothing else was different, I might not be rich. And or whatever else you're visualizing. It's a principle of magic and wizardry and sorcery. What else? What was I going to think here? There's also something about sixth sense, perception of things that are not seen, heard, touched, felt, touched, tasted, or smelled, based on just intuition. And things can be intuitively connected in real life that are remote, meaning not in the same place. I can sense if someone, let's say my dog gets hit by a car, I can sense that even though I'm not there to see it physically. I can sense, oh my gosh, something's wrong, my dog got hit. And it's not, I wasn't there, it was remote because I wasn't at the scene to see it with my 12, or sense it with my 5 senses. I sensed it with my 6th sense, even though the dog was far away and I wasn't there. And we also sense things such as being observed. We sense being watched, even if we're watched in a remote situation. In other words, you put 2 people miles away, a room right next to mine, and some or because I somehow there's a quantumness to thought, spirituality, and things of such like that. I don't understand it all, but then again, I'm not sure anybody does, at least anybody human. And I'm just throwing some ideas out based on what I've learned and studied and whatever. And I haven't done this particular topic in a video yet, so I just think it's interesting. I had 3 physics professors of note at Harvard College. I had Professor Peterson, Professor Eckert, and Professor Wagner. If you want to deep dive me, I guess you could go back to search Harvey Mudd and see if those three professors were teaching in the 80s. I started going to Harvey Mudd in 84. I was class of 88, but I dropped out in 87. To me, math is like the literature of science, whereas physics is like the philosophy of science. Physics is very, esoteric, what do you call it? Existential, very, very, very philosophically based or implying, whereas math is more literature, storytelling, and writing literal, puzzles and things that are more concrete. And it's easier. I've talked about math a lot in my videos because it's more concrete. It's easier to speak of, but physics becomes more abstract and more theoretical than just straight math a lot of the time. Anyway, I hope you guys enjoyed this lesson, and let me